again. Like we got some great things on the show today.
It's Kate BYP back in the antenna saddle, and the latest edition of IEEE Antennas and Propagation magazine has come along with the boundary element method. I'm going to use this to get you onto the topic of how to make end feds and verticals work. The way amateurs do them, they suck with great suction. I'm going to show you how to fix that. Here we have a diagram. Consider an ideal metallic body illuminated by a known excitation electrical field, E field, which can be expressed. We can express it as an excitation potential. The lines E, EXC excitation, V voltage excitation come from those field lines. Those field lines are falling on that surface that looks like a sand trap on a golf course. That's some metallic surface. The relationship is E excitation equals the negative of nabla times V EXC. What's hiding in that nabla term is the complex math differential equations and why computers and big computers are needed to calculate electromagnetics and antennas, because that symbol is implying summing up all the charges on that oddly shaped body. This is where the idea of calculus comes along, to calculate the area and the total charge on that body, but we can't do that because it's a screwball shape. We don't know what the equation of that shape is to calculate a surface integral. An excitation field, E sub EXC, creates a surface charge density rho sub S on a body. And there's rho sub S. The potential can be known and imposed by external circumstances. A battery connected or grounded body, or unknown and to be determined, an isolated body. But in all cases, it remains constant inside the body and on its surface. Did you catch that? There's something extremely interesting there. Notice the body can be isolated in free space, or it can be the surface of the ground, or it can have a potential applied to it. What does that tell us? If we think about that, something really, really interesting pops up. I'll leave that to you to ponder. Remember, external circumstances, a battery connected or grounded body. As a result of the excitation, an unknown surface charge density, rho sub S, appears on the surface of the body. This charge produces an induced electric field potential. Induced. The field lines come and they induce something in the body. In electrodynamics, the adjective induced is replaced by scattered. You've probably heard me talk about scattering. We don't like scattering in antennas. That means it scatters energy to the four winds. Skipping over the math is becoming increasingly ugly. In general, either the body has a known potential U being connected to a battery or grounded. There's that thing to focus on again. Does something jump out at you about that? What if it's a charged ground? Or has a known total charge Q isolated body? Yada, yada, yada. And on they go to some horribly ugly math. This is the horribly ugly math. This is a simple version by the method of moments that simplifies it. Otherwise, you're doing a crap load of differential equations to calculate this. This is why I keep hammering on make only simple, perfectly straight wire antennas. It's a trivial problem to calculate the fields induced on a straight wire. That's just that. You try to do this, and you're going to take that computer and you're going to blow its mind. You don't want to go there. Okay, there's a setup. Not from Hobby Lobby sources. See that? That's where this ham shack comes from. 3 kinds of wire. Long wire. This is the end fed that everyone crows about. Nobody can make work. I've proven to you they're trash. Vertical monopole. This is not an end fed. It's not an end fed half wave. It's not an end fed half wave with Balint and crap. We don't make up acronyms. It is a long wire, period. No acronyms, no nonsense. Vertical monopole, we shorten that to vertical. It's obviously a monopole because it has a single pole. There is absolutely zero difference between that long wire and that monopole. Except in free space, they're oriented perpendicular, so they'll have different field responses. The electrical field dominates an antenna analysis. So if the electric field is exciting the long wire, it won't excite the monopole because they're at right angles. Skipping right along, we call this a what? Dipole. Well, it isn't. That's what we call it. There is absolutely no difference between each of those wires and that, except its orientation, and that long wire is absolutely in every way identical to both of those wires. Now that's in free space. Free space means nothing around. If there's a charge on those wires, according to principles of electrostatics, in free space, there are no field lines. Field lines don't exist just because of a single set of charges. It takes two charges coupling or an already established field the other direction to establish field lines. Why is it the dipole is very easy to make and load, and I've proven that here. And these two are such a pain in the rectum. Lots of verticals out there, very few people can ever match them. And the poor people that make long wires waste their time with balance units and various and sundry nonsense, and just end up heating up the toroid, and nobody can hear them. So what can we get from the dipole case to make those two work? Well, we can't go any further than this without at least electrical field theory. And the obvious problem here is that here's the end of a round or concentric or what we call coax line, the center conductor and the shield. And the shield's pulled off to the side and twisted. That's how I build my dipoles. But see, it's obvious that transmission line has two places to connect with on a dipole, but not with the end feds, and those are both end fed. It's impossible to feed both ends, because if we try to do that, we make a loop. If we fold the end back over, we make a folded inductor. That's not an antenna. So how do we exploit this? How do we fix this problem and get a perfect match like we do with a dipole? Well, we got to start with field basics, basic EM fields. Note right up front the contradiction. We say electromagnetic fields, we say electrical field, but the field is not electrical. There's a basic relationship for an electrical field line. Two charges, Q and Q prime. And the basic relationship is Q times Q prime, which is approximately Q squared over R squared. R is the radius or the distance between the two charges. That field line is a mechanical force. It is not electrical. So the term electrical field line is misleading. It means an electrically induced mechanical field, and it is literally mechanical force. It's described in units of dyne centimeter, and that's mechanics. Since all these charges are negative, and the laws of physics say that negatives repel because they're like, then those charges try to push each other apart. Real good treatment of this in the book University Physics by Sears and Zemansky. What becomes extremely important in antenna analysis is to understand the modification of that, which is Q prime over R squared times the cosine of the angle. And that's the angle included from normal, which is a dashed line perpendicular to the conductor, a charged surface, and where the charge is down here towards the bottom. Since it's a different charge, we'll call them Q and Q double prime. But Q double prime has moved, or perhaps Q has moved, and Q is the reference point. So the force in between the two is decreased by the cosine of theta. The cosine of 0 is 1. So the maximum field strength coupling is when the charges are in line at the top. And when the two charges are in line, as in Q triple prime, there's no field coupling. This is what blows the fantasy of that being called a dipole after the model of oscillating dipole charges out of the water. That is not a dipole because charges on that wire traveling out the wire and back cannot couple with each other. They can't make magic field lines that jump off that wire and come back as a rule. Not when we have this simple system. So as Q triple prime approaches being on that wire, the field disappears. This bottom diagram is all about what vertical monopoles are about. The problem with the vertical monopole and the end fed is that here's the end of the transmission line. There's a potential on the end of the line. Let's say it's an RF AC, but we stop time and it's at some voltage, some potential. There'll be field lines in the dielectric space in that transmission line. There'll be field lines between those wires exiting, but that's it. That's called an open circuited transmission line. There's a little bit of capacitance added to the end because the wires are coming out. It doesn't do anything useful. It basically reflects almost all the energy back to the transmitter. It's not much of an improvement to extend that center wire like either of these. That can in theory put voltage excitation on the wire, but it doesn't work. The old radio antenna handbook published by Radio Magazine in 1936 says the input resistance of a long wire can be about 2,500 ohms. Do the reflection coefficient calculation for 50 ohm versus 2,500. Calculate the SWR. It's basically infinity. That's why long wires don't work, and no combination of kludged up balons or unons or other ferrite crap is going to fix that because the wire hasn't changed. The only way to couple into that is to get some way to reference that to ground, because we can't put a feed point up there with two conductors and bring a wire down, because that's no longer a long wire. That's what we call an inverted L. That's essentially a monopole. So the problem is a shield has nowhere to go. It does in a dipole. It has two absolutely identical arms, and it works beautifully. I've proven that in my videos here. So if we're looking in the context that most antennas system analysis is done in transmit, because we have a lot of energy to work with for measuring, if a RF signal is coming out of the transmission line to this point, it hasn't yet reached the antenna. There's no antenna here. And it doesn't go any further because the shield has nowhere to go. That's not the case here. But it is the case here, and it is the case there. Only one connection. So the traditional basic answer for vertical monopoles in the ARL handbook is to put a ground stake in the ground and connect what? We can't put the shield up what we're sitting on. That would be uncomfortable and wouldn't work, so we ground the shield, and we violate the electrical code, because that's now grounding the chassis of the radio, and that's illegal. But in theory, that does make a 50 ohm feed point. That's what the old handbooks say, and it may work. So if we look at the shield as having charges, electrical charges, and it must, because it's essentially that system, charge pairs with field lines in between. What does that say about the dipole? Does it say that there is a field line concentration in between those two loops, which are the feed point? By this description here, with Q triple prime being essentially in line with the wire with Q and no field lines, what's that say about coupling from the feed point out along the wires? It says there ain't none. All the coupling is at the center. Now what happens if we do this at the so-called ground end of the monopole? Right below that circle, we put a ground rod. The antenna is almost sitting on the ground. Now we get coupling between the antenna and ground? No. We can't jump ahead of the feed point and go to the antenna. The energy hasn't gotten to the antenna yet. Without the ground connection, there's no coupling out of the transmission line, so it's open. So therefore, the ground connection is not part of the antenna, and there is no such thing as an antenna with ground radials. The ground radials are for the transmission line, not the antenna, period. It is wrong to say my antenna has ground radials. Wrong. Because the process of installing it and foolishly putting a bunch of copper wire in the ground to waste energy is part of the installation process does not mean that's how it works. What we've accomplished by grounding the shield is now we have field line coupling between the very bottom of that antenna conductor and the surface of the earth. That is not for purposes of the antenna. That is for initially coupling the energy from the transmission line into the field space between the bottom of the antenna. Think the first quarter inch of that vertical wire and the ground. Then thereafter, charges on the antenna wire can couple to the ground. That's what happens here. I made field strength measurements at low power on my 20-meter dipole. Nothing at the feed point, nothing until the ends of the wire. So that shows that the purpose is not initially for the antenna to couple to the ground because the energy hasn't reached the antenna yet. It's still coming into the feed point. So this shows that the feed point is distinctly separate from the antenna, and it is part of the transmission line, not the antenna. This shows that what's done at the feed point is not antenna tuning or not antenna matching. It is attempting to match the transmission line to the feed point. Then the next problem is going from the feed point to the antenna, then from the antenna to the field space between the wire and the ground, then to the antenna function to emit that off into space. And all those steps have to be matched. See our master's level textbook and not wannabe know-it-alls on internet ham forums. The favorite topic of folks that can't make end-feds work, they got to have a balun. Transmission line matching, not antenna matching. You will not match an antenna with a balun. If the antenna is hopelessly screwed up, it's screwed up forever. Will not work. Here's my traditionally poor artwork of that vertical monopole, transmission line coming out, ground to shield, center conductor to the bottom of the tube. We got field lines. That energy, those charges can come out of that line and carry fields with them now to start to make coupling between the vertical conductor and ground. Now, a modification of that, which incorporates the idea of a magnetic loop and a vertical monopole, is what's called shunt feeding. That combines a magnetic loop, which is the right side tube, which is the shunt, connecting at the top, going over and coming back down the antenna tube. That's a magnetic loop. And it is coupled into that vertical radiator. Just that is not an antenna. A loop is not an antenna. A loop is a single turn inductor. It has to have something to couple into or it don't do squat. And this is why when folks make the mistake of making loops and they have to put a giant high voltage capacitor at the feed point because the energy isn't going anywhere and making high voltages, and it destroyed the first few capacitors they tried to put on it, so they had to go to a bigger air variable and then bigger because of the high voltage arcing. The energy is not being transmitted. They put a tuned circuit at the feed point. It just has a high internal current, makes a lot of heat, doesn't do much of anything. The energy has nothing to couple to. Interesting to note that the fields inside the space between the two poles is 0. Therefore, this is directional. I made a 2-meter full-wave vertical like this. It showed an S5 directionality from here to south central North Carolina, about 100 miles. The vertical was on a rotor. You ever seen a single vertical on a rotor? Well, I have one, and it's highly directional. And my 20-meter vertical is also directional. It's also shunt fed. This eliminates the nonsense of ground radials. The radials are there for transmission line coupling. Once the antenna has charges, it can couple fields to the ground. In AM broadcast, they plow miles and pounds of wire in the ground to, quote, improve the conductivity of the soil. I think that's from radio antenna engineering. That's a bit different purpose. The problem with the false notion that radials are for antennas is that the higher up the charge is on that vertical pole, the worse the angle, the steeper the angle, the longer the distance, and the less coupling there is. And if you go halfway up that vertical wire, say it's 10 feet, and look down, you can't even see those 14 gauge wires anymore. Their surface area is so incredibly small. So they do nothing useful for the antenna. They're simply there for transmission line coupling. Now you want to improve that, you put down a metal plate and perch that monopole on that plate. Now you've got a big, big surface area. Far more surface area than the surface of the wire. And this is part of the discussion of what's known as grounds of zero extent, grounds of small extent, and grounds of large extent. Putting out miles of wire in the soil makes a ground of large extent, arguably. This can be a small extent. This is what I have on my pickup truck with the Hustler ball mount antenna. The antenna's on a small metal plate, and it just kicks butt. Beautiful matching on 20. I can almost work the entire band with low SWR. If we think about this, how can we adapt that to solving that problem? Think real careful about that. Play this video back if you missed it and pick up these concepts. How can we improve and make this long wire work if it's identical to the vertical monopole, except that it can't couple to the ground at the feed point? It's too far away. If we put a wire from the transmission line shield to ground, we've made another part of the antenna. And that's no longer an end-fed wire. So if you'll think very carefully, get a book on basic electromagnetics and study these field relationships, because it's absolutely vital to be able to at least understand how the E fields work. Otherwise, we can't visualize what's happening with the antennas, and all we're going to do is guess. We're going to universally guess wrong and not be able to match it and not be able to optimize it. And for bonus topic, did you know it's possible to have a correctly matched feed point and a high SWR? It is. I've proven to you in my antenna videos that the length of that dipole is critical to relate to the frequency, because the energy is traveling out the arms, being reflected, coming back, it's emitted in the process. That feed point can be correctly matched, but the wires be the wrong length, and there's still reflected energy. And the only way to tell the difference is with time domain reflectometry. If we get a reflection that's at the time of the energy arriving at the feed point, then it's a feed point mismatch. If it happens about a half wave later after going out the antenna wire and coming back, then there's something wrong with the length of the wire, or the antenna is not straight, it's bent, which is why we don't want an inverted L. They're crap also. But something is wrong. The propagation out and back the wires is wrong. There's energy that's not emitted. When it comes back, there's no place to store it, so it goes back down the transmission line. So beware if you're looking at feed point matching. It might be correctly matched and not work worth a hoot. So, a little bonus topic for you. So, happy thinking. If you think this through, you'll find some neat stuff. Kate BYP did it.